Tonight, while you sleep, the universe will quietly grow, new space appearing from nowhere between every galaxy in the sky, faster than anything has a right to move. By morning, thousands of galaxies will have slipped over an invisible line, gone beyond reach, forever, and no one on Earth will notice. We only learned this was happening within living memory, and the moment we measured it carefully, we found something wrong with the number, something that shouldn't be there. Tonight is the story of that number, the people who fought over it, and what it whispers about how all of this ends. So make yourself comfortable, subscribe if you'd like more quiet journeys like this, and come find out what we're losing and why. Part 1. 73.5. On April 10th, 2026, a paper appeared in the journal Astronomy and Astrophysics that should have ended one of the strangest arguments in the history of science. A team calling itself the H0 Distance Network had spent years weaving together the most reliable distance measurements ever made in the nearby universe, and they had produced a number with an uncertainty of barely 1%. The number was this. The universe is expanding at 73.5 kilometers per second per megaparsec. It was the most precise local measurement of cosmic expansion ever achieved. And instead of ending the argument, it made everything worse. I want to take that number apart for you slowly because it is going to be the spine of everything we talk about tonight. A megaparsec is a unit of distance, and it is an absurd one by everyday standards. It is 3.26 million light years. So, the measurement says that for every 3.26 million light years you travel away from Earth, the galaxies around you are receding from us an additional 73.5 kilometers every second. To put that speed in perspective, 73 kilometers per second would carry you from London to Paris in under 5 seconds. It is roughly 200 times faster than a rifle bullet. And here is the part your intuition will resist. That speed is not a fixed limit. It compounds with distance, slab after slab, without end. A galaxy 10 megaparsecs away, about 33 million light years, is fleeing at more than 700 kilometers per second. A galaxy 100 megaparsecs away is fleeing at over 7,000 kilometers per second, which is about 2% of the speed of light. Keep extending the line, and at a certain distance, the recession speed reaches the speed of light itself. And then it keeps going. There are galaxies in our own sky, photographed by our own telescopes, that are receding from us faster than light. That is not a mistake, and it is not science fiction, and we will spend a good part of tonight understanding exactly how that can be true. But the speed alone is not the terrifying part. The terrifying part is that we cannot agree on it. Modern cosmology has two great ways of measuring how fast the universe expands. One method works outward from our neighborhood, using stars and exploding suns as distance markers. It keeps producing values around 73. The other method works forward from the infant universe, reading the oldest light in existence and running the laws of physics ahead like a simulation. It keeps producing a value around 67.4. Those two numbers differ by about 9%, and for years, scientists assumed the gap would close as the measurements improved. The measurements improved, the gap did not close. With the error bars achieved by 2026, the probability that this disagreement is a statistical fluke is roughly 1 in a million. Let me give you one more way to hold the speed itself, because numbers this large slide off the mind unless we anchor them. Over the course of this single 2-hour video, the expansion of space will have added roughly 400 million kilometers of new distance between us and a galaxy sitting 100 megaparsecs away, which is more than the distance from the Earth to the Sun and back. Measured across the whole observable universe, the numbers stop being numbers at all. The cosmos gains volume measured in trillions of cubic light years every single day, fresh space arriving from nowhere, asking permission of no one. Nothing in your daily experience grows this way. And yet nothing about tonight will feel violent, because all of that creation happens in the emptiness between galaxy groups, far from anything bolted down. That contrast between the calm of our bound little neighborhood and the immensity of what the universe is doing at range is the mood of this entire story, and I would like you to keep it within reach as we go. Physicists call the measurement crisis the Hubble tension, which is a remarkably calm name for what it actually is. It is the possibility that the two halves of cosmology, the early universe and the present one, are not connected by the physics we believe in. One of our most trusted instruments is wrong, or our model of the cosmos is missing an ingredient. There is no third option left that anyone takes seriously. You might reasonably ask why a 9% disagreement deserves the word terrifying. Here is why. This single number sets the age of the universe. Run the cosmos backward at 67 and you get a universe about 13.8 billion years old. Run it backward at 73 and you lose nearly 1 billion years of cosmic history. This number sets the scale of every distance in astronomy, from here to the farthest galaxy. And because the expansion is controlled by a mysterious component called dark energy, this number is also wired directly into the question of how the universe ends. Whether everything drifts apart forever, or tears itself to pieces, or collapses back into fire, depends on the behavior of the expansion rate we are currently failing to agree on. So when I say the reality of cosmic expansion is terrifying, I do not mean it the way a horror film means it. Nothing tonight is going to jump out at you. I mean the slower kind of unease, the kind that arrives when you realize that the ground you assumed was solid is actually a question mark. The entire visible universe is running away from us, most of it faster than light. The flight is speeding up, and the two most careful measurements our species has ever made disagree about the rate at the level of 1 chance in 1 million. It helps to understand how much of astronomy leans on this single value, because the dependence is nearly total. The Hubble constant is the conversion factor between what we can observe about a distant object and what that object actually is. Get the constant wrong by 9%, and every luminosity in the distant universe is wrong. Every mass estimate built on that luminosity is wrong. Every timeline of galaxy formation shifts, and the calibration of the cosmic dawn moves. Cosmologists sometimes describe it as the first domino of the discipline. The number every other number must pass through on its way to meaning something. That is why two communities of careful, brilliant people have been willing to spend entire careers arguing about a 6-unit difference. They are not quibbling over trivia. They are arguing about the exchange rate of reality. There is something I find almost endearing about this crisis, and I will confess it to you up front. The most important number in existence, the one that decides the age, size, and fate of everything, fits comfortably on a postage stamp, 73.5, or 67.4, depending on whom you ask. Two little numbers, and a century of genius stretched between them, and they have started what can only be described as a polite, footnoted war. Tonight, we are going to follow that number from beginning to end. We will watch it get discovered by a man measuring smudges on glass plates, watch it get measured wrong by a factor of 7, watch a century of brilliant people fight it down to a 1% precision, and then watch that precision split physics in two. We will meet the two great clocks that disagree, and the space telescope that was supposed to settle the fight and refused to. We will meet the invisible engine pressing the universe's accelerator, and the new evidence, gathered by 5,000 robots on a mountaintop in Arizona, that the engine may be dying. And at the end, we will read the 3 possible endings of the universe, because all 3 are written in this one number. Before any of that can make sense, though, we have to go back. Because the strangest thing about the expansion of the universe is how recently we learnt it was happening at all. Just over a century ago, the finest scientific minds on Earth believed the entire universe was a single galaxy, ours floating in an infinite black nothing. The story of how fast the universe is expanding begins on a night when humanity did not yet know there was a universe to expand. And it begins, of all places, with an argument in a museum. Is less than break time equals 1s? Is greater than number part 2. The night the universe got big. In April of 1920, two astronomers stood up in the Smithsonian Museum of Natural History in Washington to debate the size of everything. The event is remembered today as the Great Debate, and the question on the table sounds almost unbelievable now. Harlow Shapley argued that the Milky Way was the entire universe, and that the little spiral smudges astronomers saw through their telescopes were just clouds of gas inside it. Heber Curtis argued the opposite, that each of those spirals was a separate island of stars, unimaginably far away, and that our galaxy was merely one among many. The greatest astronomers alive could not settle it. Nobody in that room knew whether the universe was one galaxy or billions. That was barely a century ago. There are trees alive today that are older than our knowledge that other galaxies exist. The tool that would settle the debate had already been forged quietly by a woman who was not allowed to use the telescopes. Henrietta Swan Leavitt worked at the Harvard College Observatory as a computer, which in that era meant a human being, usually a woman, paid about 30 cents an hour to measure star images on photographic glass plates. Leavitt was studying a class of stars called Cepheid variables, stars that brighten and dim in a steady rhythm, some over days, some over months. In 1912, she published a discovery of almost absurd usefulness. The slower a Cepheid pulses, the more light it truly puts out. The rhythm tells you the wattage. And once you know a star's true brightness, you can compare it to how faint the star appears from Earth and calculate exactly how far away it must be. Leavitt had turned a species of blinking star into a ruler. Astronomers call such objects standard candles, and her law remains, to this day, one of the load-bearing walls of all cosmology. Enter Edwin Hubble. He was a tall, pipe-smoking, almost theatrically self-serious man who had been a lawyer and an athlete before becoming an astronomer, and he had access to the one instrument on Earth that could exploit Leavitt's law to its fullest. The 100-inch Hooker telescope on Mount Wilson, above Los Angeles, was the largest telescope in the world. In October of 1923, Hubble was photographing the Great Spiral in Andromeda, the largest of the mysterious smudges, when he noticed a star on his plate that had changed brightness. He initially marked it as a nova, an exploding star. Then he checked older plates, found the star pulsing in a regular rhythm, realized it was a Cepheid, and crossed out his note and wrote 3 letters with an exclamation point. VAR for variable. That little annotation might be the most important graffiti in the history of science, because when Hubble applied Leavitt's law to that star, the distance came out to roughly 1 million light-years, far beyond any possible edge of the Milky Way. The smudge was not a cloud. It was another galaxy. In one measurement, the universe became unthinkably larger than it had been the night before. That alone would have secured Hubble's name forever, but the second act was stranger. For years, an astronomer named Vesto Slipher, working at a small observatory in Arizona, had been measuring the light of these spirals and finding something odd. Their light was shifted toward the red end of the spectrum, which suggested, by the same physics that drops the pitch of a passing siren, that nearly all of them were rushing away from us. Nobody knew what to make of it. A Belgian priest and physicist named Georges Lemay did know what to make of it. In 1927, working from Einstein's equations, Lemay proposed that space itself was expanding and even derived the mathematical relationship between a galaxy's distance and its speed. 2 years before Hubble published. His paper appeared in an obscure Belgian journal, and almost nobody read it. History can be careless that way, and there is a fair argument that the constant at the center of tonight's story carries the wrong man's name. What Hubble did in 1929 was supply the data that made the idea undeniable. He took Slipher's velocities, combined them with his own hard-won distances, and plotted them against each other. The points fell along a straight line. The farther away a galaxy was, the faster it was receding in direct proportion. Twice the distance, twice the speed. This is the relationship now called Hubble's law, and the number describing its steepness, the speed gained per unit of distance, is the Hubble constant. It is the number this entire night is about. I want to pause on what that straight line actually says, because it is stranger than it looks. If every galaxy is rushing away from us, it is tempting to conclude that we are at the center of some great explosion, that everything is fleeing from this particular spot. The mathematics says otherwise. A uniform expansion looks exactly the same from every point inside it. An observer in any of those fleeing galaxies would see all the other galaxies, including ours, rushing away from them with the same law and the same constant. There is no center. There is no edge that anyone has found. The whole thing is simply getting bigger everywhere at once, and the straight line on Hubble's plot was the first time a human being had caught it in the act. Here is the part of the story I find genuinely comforting, given where we are headed tonight. Hubble's first value for his own constant was about 500 kilometers per second per megaparsec. The modern value, as you know, is around 70. He was wrong by a factor of 7. The error was not carelessness. His distances were poisoned by problems nobody could have known about, including the fact, discovered decades later by Walter Bard, that Cepheids come in 2 distinct families with different brightness rules, and Hubble's calibration had mixed them together. The consequences were embarrassing on a cosmic scale. A universe expanding that quickly must be young, and Hubble's number implied a universe younger than the Earth. Geologists, holding rocks more than 3 billion years old, were happy to point this out. So the 20th century became one long argument about this number. Bade split the Cepheid families in the 1950s, and the constant fell by half overnight. Alan Sandage, Hubble's scientific heir, spent an entire career refining it downward, and through the 70s, 80s, and 90s, astronomy split into camps, one insisting the value was near 50, another near 100, each side armed with decades of careful work and a healthy contempt for the other side's error bars. It took the Hubble Space Telescope, named for the man himself, to broker a peace. In 2001, the Hubble Key Project announced a value of 72 plus or minus 8. The war over factors of 2 was finally over. And there is one more irony to collect before we move on, because it will matter enormously later. When Einstein first applied his general relativity to the cosmos in 1917, the equations told him the universe could not sit still. It had to expand or contract. Believing, like everyone, in an eternal and static cosmos, he inserted a fudge factor into his own masterpiece to hold the universe in place, a term called the cosmological constant. After Hubble's discovery, Einstein reportedly called it the greatest blunder of his life and struck it out. Keep that discarded term in mind. Near the end of the century, it is going to climb out of the wastebasket and take over the universe. Here is a detail from those years that I have always found quietly moving. Hubble himself, the man whose name the constant carries, never fully committed to what his own discovery meant. Late into his life, he allowed in lectures and papers that the redshifts might represent some unrecognized principle of nature rather than actual motion, that the universe might not truly be expanding at all. The man who handed humanity its most consequential measurement kept a private reservation about its meaning until the end. I mention this not to diminish him, but because it sets the tone for everything that follows tonight. This number has never permitted anyone, not even its discoverer, the luxury of complete certainty. A century of being wrong, then, taught us this much. Measuring the expansion of the universe is one of the hardest things our species has ever attempted, and every generation that tried it was humbled. By the early 2000s, the error bars had finally shrunk to respectability, and astronomers allowed themselves to believe the hard part was over. They could not have known that the real crisis would arrive only when the measurements became too good. Precision, it turns out, is where the trouble was hiding. But before we can appreciate that trouble properly, we need to be honest about something more basic, because almost everyone, including some textbooks, pictures cosmic expansion wrong. What exactly is expanding, and into what, and why is it allowed to outrun light itself? Is less than break time equals 1s? Is greater than number part 3? What expansion actually is? The picture most of us carry around is an explosion. A point of light detonates in a black void, debris flies outward, and the galaxies are the shrapnel, sailing through empty space away from the blast site. It is a vivid picture, and nearly every part of it is wrong. The Big Bang was not an explosion in space. It was, as best we can describe it, an expansion of space. It did not happen at a particular spot you could visit with a fast enough ship. It happened everywhere at once, including in the space your body now occupies. The galaxies are not flying through space away from some central wound. The space between the galaxies is stretching, and the galaxies are carried along like boats on a widening river, going nowhere in particular under their own power. Astronomers reach for two metaphors here, and both are useful as long as we are honest about where they fail. The first is raisin bread. Imagine a loaf of raisin dough rising in an oven. As the dough expands, every raisin moves away from every other raisin, and raisins that start out farther apart separate faster, because there is more expanding dough between them. That is Hubble's law, baked into a loaf. Dough raisin is the center of the expansion, and from any raisin you choose, all the others appear to be receding. The second metaphor is a balloon with dots inked on its surface. Inflate the balloon, and every dot recedes from every other dot, with no dot privileged as the middle. The failures of these pictures matter just as much. The universe has no crust, no oven, and no kitchen. The balloon expands into the room around it, but as far as we can tell, the universe is not expanding into anything. There is no outside for it to grow into. More space is simply coming into existence between things, which is a sentence I encourage you to sit with for a moment, because it does not get less strange with repetition. This stretching picture quietly rewrites what redshift means too. The textbook shorthand says distant galaxies are redshifted because they are moving away, like the falling pitch of a receding siren. The truer statement is lovelier. A photon travelling for billions of years rides through space that is stretching beneath it, and the photon's own wavelength stretches along for the ride. The light is not so much shifted as it is taffy-pulled by the journey itself. The oldest light in the universe, which we will meet properly in a little while, has been stretched by a factor of about 1100 since it set out, transformed from the orange glow of hot plasma into a faint microwave hiss. Every redshift in the sky is a fossil record of how much the universe has grown while that particular beam of light was in flight. Now for the question that I suspect is already forming. If space itself is expanding, is the space inside the Milky Way expanding? Inside the solar system? Inside you? The answer is no, and the reason is a matter of brute strength. Expansion is a property of the universe at large, and on local scales, it is feeble beyond description. Anything held together by a force, whether gravity binding a galaxy or electromagnetism binding the atoms of your body, simply overpowers it. The chemical bonds in a 1-meter rod would need to yield about 2 picometers per century to the stretching of space, a distance thousands of times smaller than a single atom, and they do not yield at all. the bonds win, completely and permanently. Your atoms are not expanding. The Earth is not expanding. The galaxy is not expanding. Expansion only rules in the enormous empty country between galaxy groups where gravity has grown too dilute to fight back. The proof of this hangs in our own sky. The Andromeda Galaxy sits about 2.5 million light-years away, which, by Hubble's law, should have it receding from us at a healthy clip. Instead, Andromeda is approaching us at roughly 110 kilometers per second. Our two galaxies are bound by their mutual gravity, falling toward each other through the very space that is trying to separate them, and in about 4 to 5 billion years they will merge into a single, enormous galaxy. On the village scale of our local group, gravity has won the argument forever. The expansion of the universe will never take Andromeda away from us. Remember that small mercy. Near the end of tonight, it will turn out to matter a great deal. So expansion is gentle here and irresistible at distance. And that brings us to the threshold your intuition has been bracing for. If recession speed grows with distance, without limit, then at some distance, it must reach the speed of light. It does. That distance is called the Hubble distance, and for our measured expansion rate, it sits a little over 14 billion light-years away. A galaxy at that range is receding at the speed of light. A galaxy beyond it is receding faster than light, and the volume beyond it is not some exotic sliver at the edge of things. It is almost everything. I want to be careful here, because this is the kind of claim that sounds like it should break physics. Einstein's special relativity declares that nothing may travel through space faster than light, and that law remains unbroken everywhere, always. The galaxies receding faster than light are not breaking it, because they are not traveling through space at those speeds. They are nearly at rest in their own neighborhoods, drifting at ordinary speeds among their neighbors, while the space between us and them stretches at a rate that adds up, over billions of light-years, to more than the speed of light. Relativity's speed limit is a local law. It governs races on the track. It says nothing about the track itself getting longer, and no measurement made by anyone, anywhere, would ever catch a photon being overtaken locally. The cosmic speed limit stands. The cosmos has simply found a loophole large enough to fit most of itself through. Before we count what lies beyond that threshold, one clarification will save us confusion all night. The observable universe is not the universe. It is the portion of the universe whose light has had time to reach us in 13.8 billion years, a sphere centered, for once legitimately, on us, simply because we are the ones doing the observing. A civilization in a galaxy 10 billion light-years away has its own observable sphere, overlapping ours but not identical, containing regions we will never see. What lies beyond all such spheres, nobody knows. The full universe may be enormously larger than what we observe, and many cosmologists suspect it may be infinite, in which case tonight's entire story concerns a bubble of visibility, adrift in something without edges. I find it worth saying out loud at least once. Everything we will measure, argue over, and prophesy tonight concerns the part we can see, and the part we can see may be a rounding error of the whole. You might also wonder why the numbers 46 and 14 do not match, why we can see objects 46 billion light-years away in a universe not yet 14 billion years old. The expansion is the answer to this too. The light arriving tonight from the most distant visible regions was emitted when those regions were close, and during its long flight, the space behind it kept stretching, carrying the source farther and farther downstream. The photon crossed an honest 13 billion years of travel, while its birthplace was ferried out to 46 billion light-years behind it. Even our sightlines, in other words, have been stretched while we use them. Nothing about a universe like this is allowed to stay simple, and the census we are about to take is where the simplicity truly ends, and it truly is most. The observable universe extends about 46.5 billion light-years in every direction, a sphere containing as many as 2 trillion galaxies. Run the numbers on how much of that volume lies beyond the Hubble distance, and you find that the overwhelming majority of the galaxies we can see, on the order of 19 out of every 20, are already receding from us faster than light. Sit with that census for a moment. Of all the galaxies in tonight's sky, all the spirals and ellipticals in every Hubble photograph that has ever made you stop scrolling, roughly 95%, are already moving away faster than anything we could ever send after them. Their light still reaches us, light that left them long ago when they were closer, which is its own beautiful subtlety. But the galaxies themselves, as they are now, are beyond the reach of any ship, any probe, any signal our descendants could ever dispatch, even granted infinite time. The universe is not merely large, most of it has already, in the only sense that ever could have mattered, left, and the fraction is growing. That is what acceleration means, and it is where this gets personal. The boundary is not fixed. Every year, more galaxies cross it. The universe is, in the most literal sense available to physics, getting away from us, which makes the precise speed of that getaway something rather more urgent than an academic squabble. So now you understand what is expanding and what is not, and why the speed limit survives. The scandal we can no longer postpone is this. We have 2 magnificent, independent ways of clocking that expansion, refined over decades, each checked and rechecked by people who would have loved nothing more than to catch the other side in an error. And the universe gives the 2 of them different answers. Let us meet the first clock, the one built rung by rung, from our own front porch out into the dark. Is less than break time equals 1s is greater than number, part 4. The ladder to the supernovae. There is no tape measure long enough for the universe, and no radar ping returns from another galaxy. Every cosmic distance beyond our immediate neighborhood is inferred, and the inference works like a ladder where each rung is calibrated by the rung below it. Astronomers literally call it the cosmic distance ladder, and the late universe measurement of the Hubble constant, the one that keeps insisting on 73, is a 3-rung climb. The whole structure is only as strong as its weakest rung, which is exactly why it has been attacked, tested, and rebuilt so many times. The first rung is the only direct distance measurement in all of astronomy, and it is pure geometry. Hold a finger in front of your face and blink your eyes alternately, and the finger seems to jump against the background wall. Your 2 eyes view it from slightly different positions. Astronomers do the same trick with the Earth itself, photographing a nearby star in January and again in July, when our planet has swung 300 million kilometers to the other side of its orbit. The star's tiny apparent shift against the distant background, called parallax, gives its distance by trigonometry, no assumptions required. The shifts are agonizingly small, angles comparable to the width of a coin viewed from thousands of kilometers away, and for decades parallax only worked for the nearest stars. Then the European Gaia spacecraft mapped the positions of nearly 2 billion stars with a precision that would have made previous generations weep, anchoring this first rung more firmly than ever before in history. The second rung is Henrietta Leavitt's gift, the Cepheid variables, now industrialized a century beyond her glass plates. Gaia's parallaxes reach far enough to pin down the true brightness of a population of Cepheids in our own galaxy, calibrating Leavitt's law directly. And because Cepheids are supergiant stars, tens of thousands of times more luminous than the Sun, telescopes like Hubble and now James Webb can pick them out one by one in galaxies tens of millions of light-years away, pulsing their distances out into the dark, each one a lighthouse whose blink rate announces its wattage. But Cepheids fade from view long before cosmological distances begin, so the third rung must be something visible across billions of light years. It must be one of the most violent events in nature. A Type 1, a supernova, begins with a white dwarf, the dense corpse of a dead star, an object with the mass of the Sun compressed into a sphere the size of the Earth. If that white dwarf has a companion star and steals matter from it, the corpse grows heavier and heavier until it approaches a critical threshold, about 1.4 times the mass of the Sun, known as the Chandrasekhar limit. At that mass, the white dwarf can no longer support itself, and it detonates in a runaway thermonuclear explosion that, for a few weeks, outshines its entire galaxy. The beauty for cosmology is the trigger. Because these bombs all go off near the same critical mass, they all release nearly the same amount of light, and the small variations follow rules that astronomers have learned to correct for, mostly by watching how quickly each explosion fades. A Type 1, a supernova, is a standardizable candle of almost obscene brightness, readable a quarter of the way across the observable universe. Now the climb. Geometry calibrates the Cepheids. Cepheids calibrate the supernovae by way of a few dozen precious galaxies, near enough to contain measured examples of both. Supernovae then carry the measurement out into the smooth cosmic expansion, far beyond the gravitational sloshing of our neighborhood, where galaxies ride the pure Hubble flow. Plot their distances against their redshifts, and the slope of the line is the Hubble constant, measured in today's universe from the bottom up. The most famous version of this climb is a project called SH0ES, led by Adam Rees, a Nobel laureate we will meet again in a later act, and its answer has been consistent for years. 73, plus or minus about 1. The H0 distance network, result from April 2026, the one that opened our story, is the matured version of this same approach, a web of cross-braced local measurements landing at 73.5 with that historic 1% precision. Of course, a chain of inferences is a chain of places to be wrong, and the ladder teams know their possible failure points better than their critics do. Distant Cepheids crowd together in busy starfields, where a telescope might accidentally merge two stars into one and misjudge a brightness. Interstellar dust reddens and dims starlight, mimicking distance. Cepheids, forged from different mixes of chemical elements, may pulse by slightly different rules. Supernovae, for all their standardized violence, are still individuals with scatter of their own. Each rung inherits every error of the rung beneath it, which is the quiet menace of any ladder. A 1% slip at the parallax level propagates upward and outward until it has moved the measured edge of the visible universe. It is like an error of a single millimeter in a skyscraper's foundation, shifting the roofline by a full meter. Get the bottom wrong, and you are wrong everywhere, forever in proportion. What gives the modern ladder its credibility is that it no longer stands on one foot. The SH0ES analysis anchors its bottom rung in three independent ways, and the redundancy is the point. There are the Gaia parallaxes of Milky Way Cepheids. There is the galaxy NGC4258, whose distance is known almost geometrically from water vapor orbiting its central black hole, a natural radio beacon we will properly admire later tonight. And there is the Large Magellanic Cloud, our satellite galaxy, whose distance has been pinned to 1% using pairs of eclipsing stars whose physics can be read directly from their light. Three separate anchors, three different physical principles, and the ladder built on each one independently returns the same high value. To dismiss 73 as a calibration accident, you need all three anchors to be wrong in the same direction by the same amount for unrelated reasons. Nature is rarely that conspiratorial, which is exactly why the result is taken so seriously. This is why the distance ladder community has spent 20 years essentially prosecuting itself. Every one of those systematic worries has been hunted with new instruments and independent methods, and we will watch the greatest of those hunts, the one conducted by the James Webb Space Telescope, in just a little while. But it is worth noting now that the ladder does not stand alone. Other late universe methods that skip the ladder entirely, and we will meet them soon, keep clustering around the same answer. Water vapor, orbiting the supermassive black hole of a distant galaxy, acting as a natural radio beacon, yields about 73. The warped light of quasars split into multiple images by intervening galaxies has, in several analyses, said much the same. The late universe speaks with a fairly unified voice, and what it says is 73. It is worth letting the achievement register before we complicate it. Within living memory, the uncertainty on this measurement was a factor of 2, 50 versus 100, and respectable careers burned entire decades on either side of that chasm. Today, the dispute is 6 units out of 70, measured by methods that begin from blinking supergiant stars, detonating stellar corpses, water clouds orbiting black holes, and the geometry of the Earth's orbit, all braided into agreement at the level of 1%. Whatever else tonight's crisis means, it is a crisis made possible only by extraordinary success. We have measured the speed of the universe so well that the universe has run out of room to hide its discrepancies, and that is when discrepancies become discoveries. That number would be perfectly comfortable, even boring, if not for the other clock. Because there is a second way to weigh the expansion of the universe, one that owes nothing to ladders, nothing to Cepheids, nothing to exploding white dwarfs. It does not look outward from our porch. It looks backward to the beginning and reads the universe's baby picture. And the baby picture, measured with a precision every bit as formidable as the ladders, says the ladder is wrong. Is less than break time equals 1s, is greater than number, part 5, the baby picture. Everywhere you point a radio telescope, in every direction, day and night, there is a signal. It is faint, a temperature of about 2.7 degrees above absolute zero, and it is astonishingly uniform across the entire sky. It was discovered by accident in 1964 by 2 engineers, Arno Penzias and Robert Wilson, who spent months trying to eliminate it from their antenna, at one point evicting a pair of pigeons on the theory that the noise might be droppings. The noise was the universe. It is called the cosmic microwave background, and it is the oldest light in existence, released about 380,000 years after the Big Bang. It is older than the Earth, older than the Sun, older than the disk of the Milky Way. Every second, photons from the very dawn of the cosmos end their 13 billion-year journeys in our detectors, and a small fraction of the static between channels on an old television set was this same primordial light. You have, in all likelihood, already watched the Big Bang's afterglow without knowing it. Here is where that light comes from. For its first few 100,000 years, the universe was a glowing fog, a plasma of free electrons and atomic nuclei, so dense that light could not travel in a straight line. Photons ricocheted endlessly off free electrons, trapped like light inside a star. Then the expanding universe cooled below a critical temperature, around 3,000 degrees, and the electrons settled into orbit around nuclei, forming the first neutral atoms. The fog cleared in what was, cosmically speaking, a moment. The light that was in flight at that instant has been travelling, unimpeded, ever since, stretched by the expansion from an orange thermal glow into microwaves. When we map the cosmic microwave background, we are photographing the wall of that final fog, the surface where the universe last scattered its own light. It is, quite literally, the baby picture of the cosmos, and the baby picture has features. The temperature of the background is not perfectly uniform. It varies from point to point by about 1 part in 100,000, a mottling of slightly warmer and slightly cooler patches, and within that mottling is encoded nearly everything we know about the early universe. The pattern is not random. Before the fog cleared, the plasma was ringing. Gravity pulled matter inward toward denser regions. Pressure pushed back outward, and the contest set up sound waves, actual pressure waves, sloshing through the plasma of the entire universe. Cosmologists call these baryon acoustic oscillations, and I am fond of the plainer description. The Big Bang had a sound, and the cosmic microwave background is its sheet music, the pattern of crests and troughs frozen onto the sky at the instant the medium for the sound vanished. The reason this matters for our story is that those frozen sound waves have a known size. Physics tells us how fast pressure waves move through that plasma and how long they had to travel before the fog cleared, which means we can calculate, from first principles, the true physical size of the ripples, a distance called the sound horizon, roughly 450,000 light-years at the moment of freezing. An object of known true size, observed at a known apparent size, gives you geometry, and geometry gives you the entire expansion history between you and it. The ripples are a standard ruler, stamped onto the oldest light in the universe, and they have a fossil twin. As the universe grew, those same ripples were inherited by matter itself, leaving a faint preference for galaxies to sit at a particular separation from each other, a distance that has now stretched to about 500 million light-years. Map enough galaxies, and you can find that fossil ruler lying in the statistics, a sound wave from the first third of a million years, still measurable in the arrangement of galaxies today. Keep that fossil in mind, because a certain instrument in Arizona has been measuring it with 5,000 robotic eyes, and it will return in this story with disturbing news of its own. The Planck satellite, a European mission that mapped the microwave sky through the 2010s with exquisite precision, read all of this and delivered the early universe's verdict on the Hubble constant. 67.4 kilometers per second per megaparsec, with an uncertainty of about half a unit. Notice how brutally good that precision is. Under 1%, fully the equal of the distance ladders. And notice something else, because it is the honest fine print on everything the baby picture says. Planck does not measure today's expansion rate directly. Nothing about the microwave background tells you what the universe is doing this evening. What Planck measures is the state of the cosmos at age 380,000 years, and what cosmologists then do is run that infant universe forward through 13.8 billion years of growth inside a mathematical model and read off what the expansion rate should be now. The baby picture's 67.4 is a prediction, an extrapolation through the universe's entire life, powered by a model. The model deserves a proper introduction because it is the secret protagonist of this entire crisis. It is called Lambda CDM, and it is the standard model of cosmology, the recipe book for the universe. The recipe reads as follows. Take about 5% ordinary matter, every atom, every star, every planet, everything you have ever touched or seen. Add about 27% dark matter, an invisible substance that neither emits nor absorbs light, whose gravity sculpts galaxies, and whose identity remains unknown. Fill the remaining 68% with something called lambda, the energy of empty space itself, which we will spend an entire act on shortly. Stir according to Einstein's equations, and this recipe is a triumph, perhaps the most quantitatively successful theory in the history of science outside particle physics. It predicts the detailed statistics of the microwave sky, the cosmic abundance of hydrogen and helium, the web-like arrangement of galaxies across billions of light-years, all from a handful of numbers. When cosmologists run this recipe forward from Planck's baby picture, they are not guessing. They are using the best tested cosmic model humanity has ever built. And it answers, firmly, 67.4. There is one small numerical coincidence hiding in all of this that delights me, And since we are being thorough tonight, you deserve it. Take the Hubble constant and flip it over. 1 divided by the expansion rate, and the units work out to a time about 14 billion years, eerily close to the actual age of the universe. The two are not the same thing, and the closeness is partly an accident of the era we live in, a consequence of the particular balance between deceleration in the universe's youth and acceleration in its middle age, which happened to nearly cancel when integrated across cosmic history. A few billion years earlier or later, the coincidence would dissolve. There is no agreed significance to it, only the small pleasure that the universe's speedometer and its odometer happen to rhyme on our watch. File it with the other suspicious generosities of our particular cosmic moment. It will not be the last one we meet tonight. So here is the collision, laid out plainly. The ladder climbs outward from our porch, rung by calibrated rung, touching real stars and real explosions in today's universe, and reads 73.5. The baby picture reads the frozen sound of the infant cosmos and grows it forward inside our best model, and insists on 67.4. The gap is about 9%. 9% sounds survivably small, so let me translate it. Run the universe backward at 73.5, and you reach the beginning about 1 billion years sooner than at 67.4. The age of everything shifts by roughly 1 billion years, several times longer than complex life has existed on Earth, appearing or vanishing depending on which clock you trust. Every distance in the cosmos stretches or shrinks by the same 9%. This is not a rounding dispute. It is two different universes, and we are being asked to choose. For years, the comfortable assumption was that someone simply had an undiscovered error, and respectable money was on the ladder, with its crowded starfields and its dust and its chain of inherited calibrations. But both camps kept sharpening their knives, and the error bars on both sides shrank below 1%, and the two distributions pulled apart until they no longer overlapped at all. Statisticians measure such disagreements in units called sigma, and this one now stands at 5 to 6 sigma, which is the territory where physics hands out Nobel Prizes for discoveries. The odds that random chance explains the gap are roughly 1 in 1 million. Two unimpeachable witnesses, interrogated for decades, refusing to budge, telling the court two different stories about the same universe. There were only ever two verdicts available. Someone is subtly, catastrophically wrong, or the model connecting the infant universe to tonight is missing a piece of physics. And so humanity did the only reasonable thing. We built the most powerful space telescope in history, and we sent it, in part, to find out who was lying is less than break time equals 1s is greater than number, part 6. JWST, the referee that refused to pick a side. The James Webb Space Telescope unfolded itself 1.5 million kilometers from Earth in early 2022, with a gold-plated mirror 6.5 meters across, and a sensitivity to infrared light that made it, overnight, the most powerful eye humanity has ever opened. Most of the public conversation about Webb concerns the early universe, the first galaxies, the atmospheres of distant planets. But tucked into its mission was a task with the flavor of a detective assignment. The two suspected weaknesses of the distance ladder, the crowding of Cepheids in busy starfields and the dimming veil of interstellar dust, are both problems that infrared vision and a sharper mirror directly attack. Dust scatters blue light far more than infrared, so Webb sees through the veil. And Webb's resolution separates stars that Hubble saw as merged smudges. If the ladder's 73 was built on crowded, dusty mistakes, Webb would expose it within a few years. Everyone understood the stakes. The referee had been dispatched. The SH0ES team, the ladder's chief architects, aimed Webb at more than 1,000 Cepheids across the very galaxies their measurement depends on, stars previously measured by Hubble, now re-examined with triple the sharpness. If crowding had contaminated the old photometry, the new measurements would shift. They did not shift. Star by star, galaxy by galaxy, Webb's cleaner, sharper Cepheids agreed with Hubble's, and the team's value of the constant stayed planted at 73. The single most popular mundane explanation for the Hubble tension, the one whispered at conferences for a decade, that the Cepheids were quietly corrupted and the whole crisis would dissolve in better optics, was tested directly, and it died. The crisis was not in the stars. But the referee had a second whistle to blow, and this one complicated everything. Wendy Friedman, of the University of Chicago, one of the most respected distance measurers alive, the astronomer who led the original Hubble Key project that settled the old wars in 2001, has long championed a different second rung for the ladder. Instead of Cepheids, her Carnegie-Chicago program uses the tip of the red giant branch, a method built on a lovely piece of stellar physics. Old red giant stars grow steadily brighter until the moment their cores ignite helium, and that ignition happens at a nearly universal brightness, a ceiling that is the same from galaxy to galaxy. Find the brightest red giants in a galaxy's outskirts, and you have found a standard candle, one that lives in clean, uncrowded, dust-poor neighborhoods, far from the messy star-forming regions where Cepheids dwell. It is, by any reasonable argument, a beautifully complementary check. And Friedman's tip of the red giant branch measurements with Webb have tended to land near 70 between the warring camps, close enough to the baby picture's 67 to keep alive the possibility that the tension is partly a measurement problem after all. Then her team found something genuinely unsettling. Comparing methods within the same galaxies, they reported a discrepancy between the distances implied by red giants and those implied by Cepheids, the two rungs disagreeing with each other about the same objects. Let me say that more plainly. The argument is no longer just between the early universe and the late universe. There are hints of a quieter argument inside the ladder itself, rung against rung. If that discrepancy survives scrutiny, then at least one of our most trusted standard candles is subtly miscalibrated in a way that 2 generations of cross-checks have failed to expose, and the foundations of every local distance in astronomy would need re-auditing. The referee, sent to catch one liar, came back with evidence that the witnesses might be contradicting themselves in ways nobody had fully mapped. I want to pause and appreciate the human texture of this, because it is easy to imagine science as a machine that converges smoothly on truth. What has actually happened is rival teams, led by people who have spent 40 years disagreeing with each other, sharing data, visiting each other's analyses, and slowly agreeing on the distances to individual galaxies, while still disagreeing about the constant those distances imply. The disagreement has been compressed, refined, and purified, but not resolved. This is science working exactly as designed, in public, with its seams showing, and the seams are where the universe might be hiding something new. Meanwhile, the independent juries kept filing in, the methods that bypass the ladder entirely. In a galaxy called NGC 4258, clouds of water vapor orbit the central supermassive black hole and beam microwaves at us like natural radio beacons, allowing a nearly geometric distance measurement. No candles required. Verdict: about 73. Gravitational lensing offers another route. When a massive galaxy sits between us and a distant quasar, its gravity bends the quasar's light into multiple images, and because each image's light follows a path of different length, flickers in the quasar arrive at different times in each image. The delays, measured in days, encode the absolute scale of the light paths across billions of light years. Verdict from several such analyses, again near 73, though with error bars that have widened under more careful treatment of the lensing galaxies. Method after method in the present-day universe keeps gravitating to the high value, while the infant universe, read through the standard model, calmly repeats 67.4. And then there is the newest clock of all, the one that may eventually settle everything because it owes nothing to light. When two neutron stars spiraled together in 2017, an event called GW170817, the collision shook the fabric of space-time itself, and detectors on Earth recorded the ripples. Here is the miracle. The shape of a gravitational wave signal tells you, from pure general relativity, how much energy the collision emitted, which means the faintness of the ripples at Earth tells you the distance directly. No parallax, no Cepheids, no supernova calibration, no model of the early universe. Astronomers call such events standard sirens, and that first siren yielded a Hubble constant near 70, with error bars too wide to take sides, but from a channel of information that is completely, gloriously independent of everything else in this story. The siren era is now accelerating. In February of 2026, physicists demonstrated a method using the faint background hum of countless overlapping gravitational waves, stochastic sirens, to clock the expansion. And this year brought the first joint analysis, combining dark sirens from the latest gravitational wave catalogue with the Dark Energy Survey's enormous maps of cosmic structure, weak lensing, and galaxy clustering folded together with space-time's own ringing. The third clock is being assembled in front of us, and within a decade it should be precise enough to break the tie. Let me linger one moment on those lensed quasars, because the method deserves more admiration than a passing verdict. A quasar is the blazing core of a distant galaxy, powered by matter falling into a supermassive black hole, and it flickers, brightening and dimming irregularly like a candle in a draught. When a massive galaxy sits in the line of sight, its gravity bends the quasar's light along several distinct paths, producing multiple images of the same object arranged around the lens like jewels. Each path has a different length, so each image is a delayed broadcast of the same flickering. And by matching the flickers, astronomers read the delays directly, days or weeks between copies of the same event. Those delays measure the absolute scale of a light path, billions of light-years long, with no ladder anywhere in the argument, a cosmic surveying trick conducted entirely with gravity and patience. The early results from the H0 lensing collaborations landed near 73 with confidence, then widened their error bars after harder scrutiny of how matter is arranged inside the lensing galaxies. The method's jury is still deliberating, which is itself worth noting. In this field, even the juries get cross-examined. There is also a possibility that deserves a sentence before we crown any villain, because it haunts the whole act. Both numbers could be right. 67.4 could be the true expansion rate the infant universe was destined to produce, and 73.5 could be the true expansion rate of the universe we actually inhabit, and the contradiction would then live not in any telescope, but in the 13 billion years of physics connecting the two in the model itself. Under this reading, every measurement tonight is correct, every error bar honest, and the discrepancy is the most expensive kind of truth, the kind that requires new ingredients in the universe. Hold that thought through everything that follows, because the rest of tonight is, in one way or another, an interrogation of it. Which brings us to April 10th, 2026, where our story began. The H0 distance network folded the matured local measurements into one cross-braced result, 73.5, uncertainty under 1%, and the tension did not soften. It hardened. Follow the arc of the last decade, and the pattern is unmistakable. Every time a measurement improved, every time a systematic error was hunted down and eliminated, the disagreement survived and sharpened. Errors do not usually behave this way. Errors, when besieged by better data, shrink. This thing has been besieged by the finest instruments our species has ever built, and it has not shrunk. And when a discrepancy refuses every opportunity to be a mistake, scientists begin, carefully, almost reluctantly, to treat it as a message. Suspicion turns away from the telescopes and toward the universe, toward the one component of the cosmic recipe that was always too strange to be comfortable, the invisible engine that controls the expansion rate itself. That engine was discovered in 1998 by two teams of rivals who set out to measure how quickly the universe was slowing down. The universe had other plans. Is less than break time equals 1s is greater than number, part 7, the discovery that broke gravity's brakes. Everything we have followed tonight, the warring clocks, the ladder, the baby picture, all of it orbits one question: what sets the expansion rate? The number 73.5 is not a law of nature. It is a reading on a speedometer, the speed at this moment of a universe whose pace has been changing for 13.8 billion years. And you cannot understand why the speedometer reads what it does, or why two flawless measurements of it disagree without meeting the thing that has its foot on the accelerator. So let me take you back to the 1990s, when cosmology was certain about exactly one thing regarding the future, and that one thing was about to be demolished. The logic of the time was impeccable. The universe is expanding, and the universe is full of matter, and matter gravitates. Every galaxy pulls on every other galaxy, and all that pulling should act as a brake on the expansion. The universe must be slowing down. The only question worth asking, it seemed, was how hard the brakes were being applied, because the answer would reveal the future, enough matter, and the expansion would someday halt and reverse into collapse. Too little, and the universe would coast outward forever, slowing eternally, but never stopping. Two teams set out to measure this deceleration using the Type 1, a supernovae you already know, those standardized white dwarf detonations visible across billions of light years. One was the Supernova Cosmology Project, led by Saul Perlmutter in Berkeley. The other was the High Z Supernova Search Team, led by Brian Schmidt, with a young Adam Riess, the same Riess whose ladder dominates our story tonight. They were rivals in the open, competitive sense, racing each other to the same prize, which is precisely what makes what happened next so convincing. Both teams found the same impossible thing. The distant supernovae were too dim, fainter than they had any right to be, by amounts small enough to require exquisite care and large enough to be undeniable. Too dim means too far away, and too far away means the universe has expanded more than the steady braking scenario allows. Both teams checked dust, checked supernova evolution, checked everything two paranoid rival collaborations could think to check, and reached, in 1998, the same conclusion. The expansion of the universe is not decelerating, it is accelerating. The cosmic brakes are not merely weak. Something is pressing the accelerator, overpowering the combined gravity of every galaxy in existence. The discovery shared the 2011 Nobel Prize in Physics, and it deserves a place on the short list of the greatest scientific shocks ever recorded, because nobody, including the discoverers, wanted it. Both teams assumed they had erred. Their own data dragged them, resisting, to the conclusion. And here, the wastebasket of history rustled. You will remember the term Einstein, inserted into his equations in 1917 to hold a static universe in place. The cosmological constant, the one he supposedly called his greatest blunder after Hubble proved the universe was moving. Look at what the cosmological constant actually does in the mathematics, and a chill of recognition arrives. It describes an energy belonging to space itself, every cubic meter of vacuum carrying the same small, fixed allotment of energy, and energy of that kind generates, in general relativity, a repulsive gravitational effect. The fix Einstein invented to stop the universe from moving is exactly the kind of entity that would press its accelerator. 8 decades after he discarded it, his blunder was retrieved, dusted off, and installed at the center of cosmology, where it now goes by the Greek letter lambda, the capital L in lambda CDM. We also gave it a plainer name, dark energy. Tally the cosmic books, and the result is humbling. Dark energy constitutes about 68% of everything that exists, with dark matter taking 27%, leaving 5% for every atom in every star, planet, and person. The component that dominates the universe is the one discovered last, and the one we understand least. We named the engine. Nobody has yet seen inside it. Now I owe you the resolution of a paradox, one that confuses nearly everyone who looks closely at this subject, because it sits right at the junction of dark energy and our central number. You would think accelerating expansion means the Hubble constant is increasing. It is not. The Hubble rate, the kilometers per second gain per megaparsec, has been falling since the dawn of time, and it is falling still. In the early universe, it was enormous, and it has declined ever since, even as the expansion accelerates. How can both be true? Think of the constant as a percentage growth rate, like interest on an account. That percentage has been dropping for 13 billion years. But here is the trick of compound growth. Any fixed percentage, applied to an ever-growing balance, produces ever faster absolute growth. Individual galaxies, meanwhile, ride away on distances that keep increasing. So each galaxy's actual recession speed climbs over time, even as the rate per megaparsec declines. What dark energy changes is the ending of that decline. Matter thins out as space grows, so matter's contribution to expansion fades toward nothing. But if dark energy is truly Einstein's constant, a fixed energy per cubic meter, then new space arrives carrying the same energy as the old, and the Hubble rate cannot fall to zero. It settles toward a floor, a permanent percentage growth rate of roughly 55 to 60 kilometers per second per megaparsec, and the universe becomes a balance growing at fixed interest, doubling in scale on a clockwork schedule of roughly every 11 to 12 billion years, forever. The fall of the Hubble rate and the acceleration of the cosmos are not contradictions. They are the same sentence read at two different scales, and dark energy is its author. As for what dark energy actually is, the honest inventory of candidates is short and strange. It may be exactly what Einstein wrote down, the intrinsic energy of the vacuum itself, in which case quantum physics owes us an explanation for its value that has not arrived in a century of trying. It may instead be something physicists call quintessence, a field filling all of space the way a magnetic field fills the neighborhood of a magnet, but gentler and everywhere, with the crucial difference that a field can change over time, strengthen, weaken, decay. Or the acceleration may not be a substance at all, but a symptom that Einstein's gravity itself bends differently across billions of light years than it does across a solar system. Three families of explanation, and the entire difference between them comes down to a single behavioral question. Does the engine's output hold perfectly steady through cosmic time, or does it drift? Constant means Einstein's vacuum. Drifting means a field with a history or gravity rewritten. Everything, and I mean everything in the rest of tonight's story, turns on that one question. So when the ladder and the baby picture argue about the expansion rate, understand what the argument is truly about. The path from 67.4, at the dawn of time, forgive me, the path from the infant universe to tonight's 73.5 runs, straight through dark energy, because the model doing that extrapolation must assume how the engine behaves across 13.8 billion years. Lambda CDM assumes the simplest possible engine, perfectly constant, the same in every era. If that assumption is even slightly wrong, if the engine's output has drifted with time, then the baby picture's prediction lands on the wrong number even though the picture itself is flawless, and the entire Hubble tension becomes a symptom, the first detectable creak of a larger structure shifting. For years, that idea was one speculative possibility among dozens. Then, in the spring of 2025, on a mountaintop in Arizona, an instrument with 5,000 robotic eyes reported that it had been watching the engine across 11 billion years of cosmic history. And what it reported was that the engine may not be constant after all. The accelerator pedal, the data whispered, might be easing up, is less than brake time equals 1s, is greater than number, part 8. Is dark energy dying? On Kitt Peak in the Arizona desert stands the Mayall telescope, a workhorse built in the 1970s, which has been given one of the strangest and most consequential retirements in the history of astronomy. Its focal plane now holds the Dark Energy Spectroscopic Instrument, DESI for short, an array of 5,000 individual robotic positioners, each one a small motorized arm holding the tip of a fiber optic cable. Every 20 minutes or so, all 5,000 robots pirouette in unison, each aligning its fiber with a particular galaxy or quasar in the sky. And the instrument drinks 5,000 spectra at once, reading the redshift, and therefore the distance, of 5,000 objects in a single gulp. Night after night, the robots dance and the map grows. In its first 3 years, DESI charted the precise three-dimensional positions of roughly 15 million galaxies and quasars, the largest map of the universe ever drawn, reaching out across 11 billion years of cosmic history. The purpose of the map is the fossil you already know. Those frozen sound waves from the universe's first 380,000 years, the baryon acoustic oscillations, left their ruler stamped in the arrangement of galaxies, that faint preference for pairs, separated by what is now about 500 million light-years. Here is the move that makes DESI so powerful. Find that ruler among nearby galaxies, and you measure the expansion of recent epochs. Find it among galaxies whose light left 7 billion years ago, and you measure the expansion of the middle-aged universe. Find it in the most distant quasars, and you measure the youth. The same ruler, recovered era after era, traces the entire growth curve of the cosmos, which means DESI is not just measuring how fast the universe expands. It is measuring the history of the accelerator pedal itself, the behavior of dark energy across cosmic time. The instrument is, in the most literal sense, an engine diagnostic. The first warning shot had actually come a year earlier. In April of 2024, DESI's analysis of its first year of data produced a result that made cosmologists sit up in their chairs, a mild but unmistakable preference, when combined with other datasets, for a dark energy that changes. The sensible reaction at the time, and most of the field had it, was caution. 1 year of data, modest significance, and an extraordinary claim, history is littered with 3 sigma hints that evaporated under more data, and the smart money said this one would evaporate too. The collaboration itself urged patience and went back to work, the robots dancing through another year of nights, the map more than doubling. Everyone understood the test being run. If the hint was a fluke, the larger map would dilute it toward nothing. If it was real, the larger map would sharpen it. On March 19th, 2025, the collaboration released its analysis of those first 3 years, and cosmology has not quite been the same since. Taken entirely alone, DESI's map remains consistent with the standard model and its perfectly constant lambda, and honesty requires that caveat stated plainly and remembered. But cosmologists never take one instrument alone when they can cross-examine several, and when DESI's map was combined with the baby picture, with the supernova catalogues, and with weak gravitational lensing surveys, the datasets together began to prefer something else. They prefer a dark energy whose strength changes with time, a possibility physicists parameterize with a model called W0WA, which you can think of simply as allowing the accelerator pedal to move. The statistical preference for the moving pedal over the constant one ranged from about 2.8 sigma to 4.2 sigma, depending on which supernova catalogue was used. In plainer terms, betting odds against fluke, ranging from roughly 1 in 200 to better than 1 in 20,000, impressive, suggestive, and still short of the 5 sigma standard at which physics declares discovery. The collaboration said exactly that, with discipline. But the year before, with 1 year of data, the same hint had appeared at lower significance, and skeptics had reasonably expected more data to wash it away. More data arrived, more than doubling the map, and the hint grew stronger. That is precisely what real signals do, and precisely what statistical flukes tend not to, and the substance of the hint deserves to be said slowly. The combined data suggest that dark energy was somewhat stronger several billion years ago and has weakened since by perhaps 10%. Through late 2025, the Dark Energy Survey in Chile, an entirely separate program with its own instrument and its own analysis, reported its own data leaning the same direction. If these readings hold, the engine that dominates the universe is not Einstein's eternal constant. It is dynamic, it has a history, and lately it has been easing off the accelerator. The universe would still be expanding, still even accelerating for now, but the foot on the pedal is lifting. 68% of everything that exists may be in the early stages of a change whose destination nobody knows. The reaction across the field tells you how seriously this is being taken. Senior cosmologists, people professionally allergic to overstatement, describe the DESI results in public with phrases like "another mind-blowing change," and the leadership of rival surveys began openly discussing whether the standard model of cosmology needs modification. None of them declared a discovery, and that restraint matters. But there is a tone you learn to recognize in science, the tone of a community quietly rearranging its furniture in case something large is about to move in. And that tone has been audible in cosmology since the spring of 2025. The instrument builders responded in the way instrument builders do. DESI continues collecting toward a final map of more than 40 million objects. Europe's Euclid Space Telescope is surveying billions of galaxies for exactly this question. The verdict is being purchased with hardware, and it will arrive within years, not decades. There is a technical wrinkle buried in the best-fit solutions that theorists find genuinely alarming, and it earns one paragraph. The fitted histories tend to have dark energy crossing a boundary physicists call the phantom divide, behaving on one side of it in early epochs, and the other side more recently. The trouble is that the simplest theoretical machinery for dynamic dark energy, a single evolving field rolling down an energy slope, cannot gracefully cross that line. Either nature is using machinery more exotic than our simplest models, multiple interacting fields, modifications of gravity itself, or the crossing is an artifact, a sign that we have stitched datasets together slightly wrong. The phantom crossing is either the first outline of genuinely new physics or a seam showing in our analysis, and nobody currently knows which. I will flag everything in this region of tonight's story the same way. These are hints at the 2.8 to 4.2 sigma level, not established fact. Systematic errors could still be lurking in any of the combined datasets. The next DESI releases, and the enormous surveys coming behind it, will harden or dissolve all of it within a few years. But notice what the hint does to our central mystery the moment you entertain it. The Hubble tension exists because the baby picture, run forward through a model with a constant engine, undershoots the measured expansion of today's universe. If the engine actually varies, that extrapolation was never going to land correctly, no matter how flawless the photograph. Evolving dark energy does not automatically reconcile the numbers, and in its simplest forms, it even pulls mildly the wrong way, but it cracks open the door that lambda CDM had bolted shut. It says the recipe book may be missing a line, that the connective tissue between the infant cosmos and tonight may need rewriting. The two great anomalies of modern cosmology, the clocks that disagree and the engine that seems to drift, may be a single anomaly seen from two angles, one message arriving by two couriers. And there is a second consequence, the one that earns the word terrifying in our title honestly. Whatever dark energy is doing sets not only the present expansion rate, but the entire future of the universe, every possible ending, every fate available to everything that exists. If the engine is dying, the futures on the menu change. Before we read those endings, though, due diligence demands one last detour. We must eliminate the remaining mundane suspect, the possibility that nothing is wrong with the engine or the model, and the problem is simply where we live. What if our whole corner of the cosmos is lying to us? Is less than, break time equals 1s, is greater than, number, part 9, local illusions and dead ends. The most disarming solution to the Hubble tension is also the easiest to explain at a kitchen table. Suppose our galaxy happens to sit inside an unusually empty region of the universe, a sparse county where matter is thinner than the cosmic average. Gravity around such an underdensity would behave in a particular way, with matter steadily draining outward toward the denser surrounding walls, and that outward drainage would add itself to the cosmic expansion as seen from inside. Galaxies near us would appear to recede a touch faster than the true universal rate. Our locally measured Hubble constant would come out high, not because the universe expands at 73, but because our neighborhood does. There is real evidence that such a region exists. Galaxy counts suggest the Milky Way may reside in a sparse zone called the KBC void, possibly 2 billion light-years across, one of the larger recognized structures in the nearby cosmos. The idea is taken seriously, has able defenders, and would be wonderfully deflating, the great crisis of cosmology reduced to a complaint about the neighborhood. The trouble is arithmetic. When the supernova samples are analyzed across their full range, reaching far beyond any plausible local bubble, the high value persists, and most published analyses conclude the void can shave only a unit or two off the local measurement, not the 6 required. The illusion is probably real and probably minor, a thumb resting lightly on the scale, not the answer. A stranger cousin of this idea deserves one breath, because it is one of those minority proposals that refuses to die. It is called timescape cosmology, and it begins from something true. Clocks tick at different rates in different gravitational environments, and time inside sparse voids genuinely runs at a slightly different rate than time in galaxy-filled walls. The timescape proposal suggests that when you account for billions of years of this patchwork, averaged across an honestly lumpy universe, the appearance of accelerating expansion can emerge without any dark energy at all. The acceleration as a kind of bookkeeping mirage produced by comparing clocks that were never synchronized. Most cosmologists judge that the standard treatment of the lumps is adequate and that the mirage is far too small, but the idea survives at the margins, periodically claiming a better fit to one supernova compilation or another, a genuine fringe theory in the original, respectable sense of the term. If it were ever vindicated, nearly everything in tonight's final act would be rewritten, which is reason enough to know it exists, and the long odds against it are reason enough to move on. And one historical alternative deserves its brief obituary, because its failure is a quiet triumph for everything else tonight. From the 1920s onward, skeptics of expansion proposed that light might simply tire, photons shedding energy on their long crossings, reddening with distance in a perfectly static universe. Tired light was a respectable hypothesis once, and the universe itself refuted it on 2 clean counts. Distant supernovae visibly run in slow motion, their weeks-long brightenings stretched exactly as expansion predicts, where tired light predicts no stretching of time at all. And the cosmic microwave background arrives as a mathematically perfect thermal spectrum, which expansion preserves naturally and energy-leaking photons could not. Every alternative that abandons expansion has died on similar evidence. the stretching of space, is among the most thoroughly confirmed facts in science. The argument was never about whether, only about how fast, and lately about where the pedal is heading. While we are conducting due diligence, intellectual honesty requires admitting the strangest entry in the case file, one that cuts the other way entirely. Quantum field theory, the framework underlying all of particle physics, can be asked to estimate the energy of empty space, the very quantity dark energy seems to be. The estimate comes out too large, by a factor of 10 to the power of 120, a 1 followed by 120 zeros, the most spectacularly failed prediction in the history of physical science. The honest summary is that our best theory of the small predicts a vacuum violent enough to shred the cosmos instantly. The universe presents instead the gentlest push ever measured, and nobody knows why. I include this so the stakes are calibrated. The number at the center of tonight is one humanity has measured to 1% and mispredicted by 120 orders of magnitude. So the mundane suspects have been questioned, and the case stands as follows. The void is real but too shallow. The exotic accounting of timescape remains a long shot at the margins. The expansion itself is beyond reasonable doubt, certified by slow-motion supernovae and the perfect thermal glow of the infant sky, which leaves us exactly where the evidence has been pointing all night. 73.5 is not a neighborhood illusion to be explained away, and the drift in the engine is not obviously a mirage. The number is a message, and a number that decides the growth of the cosmos is, if you read it forward far enough, a prophecy. So, let us finally read it forward. Let us watch what the expansion, at this speed, accelerating as it does, will do to the sky itself, and to everyone who looks at it after us. Is less than break time equals 1s, is greater than number, part 10, the sky that empties. Earlier tonight I left a number with you and promised it would return. Of all the galaxies in the observable universe, roughly 19 out of every 20 are already receding from us faster than light. When I first said it, that was a statement about the present, a census of where everything stands tonight. Now I want you to feel it as a statement about the future, because acceleration means that census is not stable. The boundary of reachability is not fixed. It is closing in, and every year that passes, more of the universe slips across it, out of reach, forever. The expansion rate we have spent the whole night measuring is, among its other duties, the speed at which the universe is being subtracted from us. Here is the mechanism, and it follows from nothing more than the acceleration you already understand. If dark energy is truly constant, then there exists around us a boundary called the cosmic event horizon, currently somewhere near 16 to 17 billion light-years away. Its definition is simple and absolute. A galaxy beyond that distance can emit light tonight, aimed straight at us, travelling at the only speed light knows, and that light will never arrive. Not in a billion years, not in a trillion, not ever. The photon is perfectly faithful. It crosses space toward us without pause. But the space it has yet to cross is stretching, all of it at once, and beyond the horizon, the stretching manufactures fresh distance, faster than the photon consumes it. Picture a runner on a treadmill whose belt accelerates without limit. The runner never tires and never slows, and the finish line recedes anyway. Every galaxy beyond 16 to 17 billion light-years is, as of tonight, in that condition with respect to us. Whatever happens there now, no telescope of ours, however perfect, however patient, will ever see it. Their present has been censored from our future permanently by the speed we have been measuring all night. We can still see such galaxies, which sounds like a contradiction and is instead a melancholy subtlety. The light arriving from them tonight is old light, emitted billions of years ago when they were closer and the horizon had not yet passed them. We see their youth, the era when their light could still win the race. Their middle age and everything after is the censored part, and the horizon keeps claiming new territory. Each year, on the order of tens of thousands of galaxies cross the event horizon, each crossing as quiet and as final as a door closing in an empty house. Galaxies full of stars. And, if the universe is as generous with life as its size suggests, full of other things too, each one sending its last deliverable photons toward us as it goes. The mail is still arriving from senders who can never write again. I want to make the strangeness of that boundary fully concrete, because it is the strangest border in physics. The event horizon is not a wall, not a place, not anything a traveler would notice crossing. A civilization in a galaxy sliding over the horizon tonight would observe nothing unusual, their stars shining, their physics intact, their own sky full of neighbors. The border exists only in the relationship between them and us, a quiet severing of all possible future contact, unmarked by any local event whatsoever, and the censorship is mutual and democratic. We are crossing their event horizons exactly as they cross ours, our galaxy's light failing, tonight to commit to journeys it can never complete in their direction. Somewhere out there, if other minds keep catalogues, the Milky Way is an entry quietly moving from the column of the reachable to the column of the lost. Run the clock forward, and the subtraction becomes total. Our local group is exempt, you will remember, gravity having won its local argument forever. Andromeda arrives in 4 to 5 billion years. The two great spirals folding into a single elliptical galaxy astronomers have already named Milkomeda, and over tens of billions of years the smaller neighbors fall in as well, one consolidated island of perhaps 1 trillion stars. Everything beyond the island is on the outbound tide. The galaxies of the Virgo cluster, the great filaments and walls, every spiral in every photograph that has ever made you pause, all of it recedes, fades, and reddens away. By roughly 100 to 150 billion years from now, every galaxy outside our own merged island will have been stretched beyond the reach of any conceivable detector, their light shifted to wavelengths longer than any instrument could distinguish from nothing. Even the cosmic microwave background, the baby picture itself, will be stretched toward wavelengths comparable to the size of the observable universe, the oldest photograph dissolving into the static of space itself. The sky will hold one galaxy, ours, and beyond it, in every direction, a darkness with no information in it at all. Now comes the thought I consider the quiet summit of tonight's entire story. Imagine astronomers arising in that far island universe, curious minds with telescopes finer than anything we have built, born 150 billion years from now. They survey their sky with perfect instruments and find one galaxy, theirs, suspended in an apparently infinite, apparently static void. No other galaxies, so no receding galaxies, so no Hubble's law, no hint that space expands. No microwave background, so no baby picture, no fossil sound, no evidence a hot, dense beginning ever occurred. Every observation available to them will be genuine, careful, and correct, and the cosmology they assemble from it, an eternal island of stars in a changeless night, will be wrong, not wrong through any failure of rigor, wrong because the evidence itself will have left. The expansion does not merely move galaxies. It deletes the universe's own records, and a civilization of flawless scientists, arriving late enough, would reconstruct a false cosmos and have no way, even in principle, of discovering their error. There is a touching corollary that cosmologists have actually written papers about, half in earnest. If knowledge of the wider universe is to survive into that far era, it will have to survive as records, archives passed down across spans of time that make the age of the dinosaurs look like a weekend, libraries copied and recopied for 100 billion years by whoever or whatever comes after the readable sky. The far future's cosmologists will face a choice our era never has to make. Whether to trust ancient documents describing 2 trillion galaxies and a glowing infant sky, none of which their own flawless instruments can confirm. Knowledge of the expansion, in other words, will eventually become an heirloom, a story civilizations either keep telling or lose forever. Tonight, in a small way, you are participating in the early generations of exactly that relay. You can hear the uncomfortable question hiding inside that thought, and I will not pretend it away. We are also latecomers, observing from one moment in an evolving universe. What has the expansion already carried beyond our horizon? It is entirely possible, some cosmologists would say likely, that evidence bearing on the greatest questions, regions of the cosmos, relics of the beginning, whole chapters of the early story, slipped out of reach before the first telescope was ever ground. We measure to 1% and quarrel over 6%, and all the while the library has been quietly losing volumes for 13 billion years. By cosmic standards, we live remarkably early, in a sky still crowded with galaxies and still humming with the afterglow of the beginning, the birth certificates still legible, the witnesses still on the stand. Our era is the readable chapter, and it is the expansion rate, our number, that decides how long the chapter stays readable. So the number is a prophecy, and read forward under a constant engine, the prophecy is the emptying sky, an island universe in an information desert, the long subtraction. But tonight, we learned the engine may not be constant. If dark energy is truly weakening, the treadmill may slow, the horizon may retreat, the subtraction may pause, and the ending I have just described may never happen at all, replaced by something else entirely, possibly something stranger. The honest position, as of 2026, is that the universe is offering 3 different endings, and has not yet told us which one it has chosen. It is time to read all 3. Is less than break time equals 1s is greater than number part 11, 3 endings. Every story the universe could tell ends in one of 3 ways, and which one comes true is decided entirely by the behavior of the expansion rate, which is to say, by the engine, which is to say, by the number we have been chasing since the first minute of tonight. Cosmologists have names for the 3 endings: the Big Freeze, the Big Rip, and the Big Crunch. I want to walk through each one slowly, not as a catalogue of catastrophes, but the way you might walk through 3 possible last chapters of a book you love, reading each for what it says about the story. None of them, I will tell you now, and repeat at the end, arrives anywhere near a human timescale. The universe is offering us tens of billions of safe and starry years in every version. What is at stake is not tomorrow. It is the meaning of the word eventually. Before the first chapter, a word about the steering wheel, because it will keep all 3 endings organized in your mind. You met the parameter W briefly in our discussion of phantom energy's threshold, and it is nothing more than a number describing how dark energy's push behaves as space grows. At exactly -1, the push per cubic meter never changes, Einstein's constant, and the universe freezes. Below -1, the push strengthens as space grows, phantom territory, and the universe rips. And if the quantity behind the push can weaken, fade through 0, and turn negative, the push becomes a pull, and the universe crunches. 1 parameter, 3 destinies. When DESI's combined data favor a W that drifts with time, what they are really reporting is that the steering wheel may be turning, and every cosmologist who read that paper understood instantly that the question of endings, dormant for a generation, was open again. The first ending is the one implied by Einstein's constant, the ending cosmology has treated as the default since 1998. If dark energy is exactly what lambda CDM assumes, a fixed energy in every cubic meter of space, then the acceleration never stops. The sky empties, as we watched in the last part, and the future becomes a story about fuel. Star formation runs on gas, and galaxies are spending theirs. The great star-making era of the universe is already behind us, the cosmic birth rate having fallen by an order of magnitude from its peak billions of years ago. Over the next trillion years, the remaining gas thins, the bright blue short-lived stars cease being replaced, and the stellar population reddens and dims like coals settling in a grate. The longest-lived stars, the red dwarfs, are misers of hydrogen, capable of burning for 10 trillion years or more, and they will be the last lights, glowing a dull crimson in a galaxy gone otherwise dark. Around 100 trillion years from now, give or take, the last new star ignites, and some tens of trillions of years after that, the last red dwarf exhausts itself, and the era of starlight, the entire age in which the universe makes its own light, closes. What remains is an island of remnants, white dwarfs cooling toward black neutron stars and black holes, orbiting in the dark. Let me set one scene from that long dimming, because abstractions deserve at least one picture. Imagine a planet, somewhere in our merged island galaxy, 2 trillion years from now, orbiting one of those red dwarf misers. Its sky at night is nearly starless, not because stars are absent, but because so few still shine, and the ones that do glow faint and red, embers scattered thin across the dark. Whatever stands on that planet's surface and looks up sees a galaxy in its old age, quiet, dim, settling. And here is the detail I want you to keep. That sky is still tens of trillions of years away from the true dark. The era of starlight does not end with a snap. It tapers, patiently, across a span 1,000 times longer than the universe's entire current age. The cosmos, whatever its ending, is in absolutely no hurry to reach it. Even the dark is not the end of the first ending, merely its long middle. Over spans of time I can write, but neither of us can feel, the remnant galaxy itself evaporates, close stellar encounters flinging corpses one by one into the void until the island disperses. If protons themselves decay, as some theories propose but no experiment has yet confirmed, then matter itself has an expiration date. Every atom in every cooling cinder dissolving over something like 10 to the power of 34 years or more. And the black holes, the most patient objects in existence, leak. Stephen Hawking showed that black holes radiate unimaginably faintly, and over 10 to the power of 100 years, even the supermassive ones evaporate into a thin spray of particles. The destination of all of it is a state physicists call heat death, maximum entropy, a universe stretched enormous and cold and smooth, where no temperature differences remain to drive any process, where nothing happens, and nothing can happen, forever. That is the Big Freeze. It is not violent. It is the universe as a fire that was never put out, only allowed, with infinite patience, to finish burning. There is a stillness to it that I find, against all reason, almost peaceful, the cosmos ending the way a long evening ends, by becoming quiet. Notice, too, what the expansion is doing throughout that first ending, because the freeze is the scenario in which our number completes its destiny. The Hubble rate glides down to its floor near 60 kilometers per second per megaparsec and holds there, the universe doubling in scale every 11 to 12 billion years, like an account at fixed interest, forever. The event horizon hardens into a permanent feature of reality. The subtraction we watched in the last part runs to completion. The island in the dark, the heirloom libraries, the sky that lies. In the freeze, in other words, the terrifying reality of how fast the universe is expanding never stops being true. It simply outlives everyone capable of being terrified by it, and then outlives the stars, and then outlives matter, and then runs on, indifferent, through an eternity, with no audience at all. An expansion rate with no one left to measure it, still keeping perfect time. The second ending is not peaceful, and it exists because of a question you are now equipped to ask. What if dark energy does not hold steady, but strengthens? Physicists parameterize the push of dark energy with a number called W, and the constant version sits exactly at -1. If W were even slightly below -1 permanently, dark energy would belong to a category theorists call phantom energy, with a property unlike anything else in nature. Its density would grow as space expands, the push intensifying without limit, the accelerator pressing itself harder through eternity. Robert Caldwell and colleagues worked out the consequences in 2003 and gave the scenario its name, the Big Rip, and the sequence runs as follows. In an accelerating crescendo, for billions of years, nothing seems different. Then the strengthening push begins to compete with gravity on grand scales and wins. Galaxy clusters are unbound first, their members released onto the outbound tide. Some hundreds of millions of years before the end, the strengthening push overcomes the gravity holding our merged island galaxy together, and the stars disperse like a flock losing its formation. In the final months, planetary systems unbind, worlds drifting away from their suns into the swelling dark. In the last hour, stars and planets themselves are pulled apart, the push now outcompeting the gravity that holds spheres together. And in the final fraction of a second, the crescendo reaches the small world. Molecules are torn from each other, then atoms stripped of their electrons, then nuclei disassembled, and at the last instant, the fabric of space-time itself reaches the limit of its mathematics. Expansion become infinite, in what is technically termed a future singularity. Under the old phantom estimates, with W near -1.5, the rip lay some 22 billion years ahead. I want to be completely clear about this scenario's status. It is mathematics, not forecast, a peer-reviewed exploration of what one form of dark energy would do, and the current data, you will recall, lean the opposite way toward a weakening engine away from the phantom. The Big Rip is tonight's reminder of how much hangs on a single decimal, the difference between a universe that ends in stillness and one that ends mid-sentence, and the measurement separating them is precisely the kind we keep failing to agree on. What makes the rip uniquely unsettling among the endings is not its violence, but its direction of travel. Every other cosmic catastrophe works from the top down, the large-scale structure decaying first, while the small and sturdy persists. The rip runs the other way. It begins by dismantling the largest things in existence and works inward methodically toward the smallest, saving the atom for last. There is also a cruel epistemological twist. Because the destruction accelerates, the universe would look almost normal until remarkably late. A civilization, with our level of astronomy, living 1 billion years before a rip, could measure W, notice it sitting below -1, and calculate the date of the end to good precision while their night sky still looked serene. The Big Rip is the one ending you could have on the calendar, with the stars still shining, which is exactly why the world's surveys watch that parameter the way sailors watch a falling barometer. Which brings us to the third ending, the one that was supposed to be dead, and the reason this part of tonight's story exists at all. For nearly 30 years, the Big Crunch, the universe's collapse back into fire, was a retired scenario. 1998 killed it, or seemed to. A universe whose expansion accelerates, pushed by a constant dark energy, can never turn around. Then Desi's robots delivered their map, and the combined data began to whisper that dark energy is weakening, and theorists worldwide reopened a door everyone thought was sealed, because of where a weakening curve might lead. The fitted models that describe an easing accelerator do not have to stop at zero. Several of the natural mathematical forms sail straight through it into negative territory, and dark energy, with negative strength, does not push the universe apart. It pulls it together, joining gravity rather than opposing it. In February of 2026, a widely covered calculation traced one such trajectory to its conclusion. In that scenario, the expansion continues to slow over the coming billions of years, the great outbound tide losing its conviction, until roughly 11 billion years from now the universe reaches its maximum size, pauses, in the way a thrown stone pauses at the top of its arc, and begins to fall. The whole history we have told tonight then runs in reverse. Distances shrink. The light of approaching galaxies shifts blue. The sparse sky regathers itself, the islands converging, and over the following billions of years, the contraction feeds its own momentum, galaxies merging, the background radiation compressing and heating, the universe refilling with light and then with fire, the cosmos returning the way it came, until somewhere around 20 billion years from now, everything that exists arrives together in a state of density and temperature, with no name except the one it had at the beginning. Whether such a collapse is truly an ending, or the violent seed of another expansion, a bounce, a next universe inheriting from ours, is a question the mathematics permits and the evidence cannot yet touch, and I will leave it exactly there, on the table, glowing. Picture the late stages of that third ending for a moment, because the collapse has a property the freeze and the rip lack. It is luminous. As the universe contracts, the microwave background, that stretched whisper of the beginning, compresses back toward shorter wavelengths, warming from below 3 degrees toward infrared, then toward the visible. There would come an era, far into the contraction, when the night sky itself begins to glow, faintly at first, then unmistakably, the space between the merging galaxies brightening as the universe reheats its own afterglow. Eventually the sky outshines the stars. The temperature of space exceeds the temperature of stellar surfaces, and stars begin, in effect, to melt from the outside in. The final tens of millions of years run like the first ones projected backward, plasma, fog, light everywhere, the universe ending as it began, as a furnace with no walls. And of course the oldest question in cosmology stirs at the bottom of it. The idea of a universe that collapses and rebounds, expansion after contraction after expansion, is nearly as old as the equations themselves. Considered by Alexander Friedman in the 1920s and explored by generations since under names like the oscillating universe, the bounce, the cyclic cosmos. Such models face famous theoretical difficulties, entropy accumulating from cycle to cycle among them, and nothing in the data requires a bounce. But if the crunch scenario earned its way back to the table, the cycle came with it, riding quietly in its pocket. A big crunch 20 billion years from now might be an ending in the absolute sense. Or it might be a comma, our universe, one breath in a chest that has been breathing forever. The mathematics permits both readings, the evidence selects neither, and there the matter rests, glowing, exactly where I promised to leave it. It is worth asking, before we step back, why the crunch timeline lands so soon by cosmic standards. 20 billion years is not much longer than the universe's current age, and against the trillions of years of the freeze, it is practically tomorrow afternoon. The answer is that a weakening dark energy changes the bookkeeping quickly. The acceleration we measure today is a close contest, the push of dark energy only modestly ahead of the combined gravity of all matter, and it wins only because matter keeps thinning while the push holds steady. Let the push fade even gently, and the contest tightens within billions of years rather than trillions. Let it turn negative, and both teams are pulling in the same direction, and the turnaround follows with surprising speed. In a crunch universe, the era of galaxies and stars and astronomers is not an opening act before an endless quiet middle. It is most of the show. I must now do the responsible thing and step back from all three. The crunch calculation rests on extrapolating a hint, the 2.8 to 4.2 sigma preference for evolving dark energy, far beyond the data, choosing one mathematical form among several and riding it to eternity. Other forms fit the same data and freeze. The phantom rip requires a behavior the same data lean against. The freeze requires the constancy the same data have begun to question. The completely honest summary of 2026 cosmology is this. The universe has three endings on the table: freeze, rip, and crunch, and the data are not yet strong enough to strike any of them off. And notice, please, the shape of the whole situation, because it is the thesis of tonight, stated one final way. The war over 67 versus 73, and the question of which ending awaits, are not two mysteries. They are one mystery at two timescales. Both are the single question: how fast is the universe expanding? And is the engine steady or failing? Asked once about tonight and once about eternity. Each candidate value of our number, each candidate behavior of dark energy, picks an ending the way a switch picks a track. When the number is finally settled, the ending will be settled with it. We will be the first generation in the history of thought to read the last chapter's first line. So let me ask the closing question of the night. What happens, and what will it mean, when we finally know is less than break time equals 1s, is greater than number, part 12, the most important number in existence? Let us gather the whole story into one hand. A century ago, a man at a museum podium could argue that the universe was a single galaxy, and no one could prove him wrong. Then a woman paid 30 cents an hour, found the rule hidden in blinking stars. A lawyer turned astronomer, used it to crack the sky open, and the universe turned out to be expanding. A fact we promptly measured wrong by a factor of 7. We spent 100 years repairing that number. We split the Cepheids, fought the wars of 50 versus 100, launched a telescope named after the man himself, and ground the uncertainty down below 1%, only to find that precision had been hiding the real story all along. Two flawless clocks, the ladder and the baby picture, disagree by 6 kilometers per second, per megaparsec, 5 to 6 sigma, odds of 1,000,000 to 1 against chance. The referee we sent confirmed the stars and returned with the mystery intact. The engine pressing the accelerator, 68% of everything, was caught by 5,000 robots, possibly easing off the pedal. And at the far end of the number's meaning, 3 endings wait on the table: freeze, rip, and crunch, with the data not yet strong enough to choose. That is the state of human knowledge about the speed of the universe. Tonight, as you lie there listening, here is why I believe this story is in its final act, and why the people who measure it for a living mostly agree. The instruments now arriving are not incremental. DESI's robots are still dancing on Kit Peak, with years of map yet to deliver, and its hint will harden toward 5 sigma or dissolve, one or the other, within this decade. The Vera Rubin Observatory in Chile has begun photographing the entire southern sky every few nights, an engine for finding supernovae by the hundreds of thousands where current catalogues hold mere thousands. The Roman Space Telescope will push the supernova ladder into eras no survey has touched. The gravitational wave detectors, upgraded and multiplied, will turn the trickle of standard sirens into a flood. Thousands of spacetime's own distance markers, a clock owing nothing to any ladder and nothing to any model of the infant cosmos, the independent arbiter this argument has waited for, and the background hum of stochastic sirens behind it. Within 10 or 15 years, the tension between 67 and 73 will almost certainly be resolved, and there are only 2 ways it can go. The first way is deflating and would still be historic. Somewhere in the chain, in a calibration, in a dust correction, in the disagreement between red giants and Cepheids that Webb has already flagged, a systematic error finally surfaces, the local value slides towards 68, and lambda CDM survives, vindicated to a precision no cosmic model has ever enjoyed. If that happens, Honor demands we salute it, because it will mean our recipe for the universe, 5% matter, 27% dark matter, 68% constant lambda, held firm under the most sustained quantitative siege in the history of science. The second way is the one every physicist quietly hopes for, because it is the interesting one. The tension stands. The sirens come in high, beside the ladder. The error hypothesis dies of exhaustion, and cosmology is formally short one ingredient. Early dark energy in the universe's first instance, a drifting engine of the kind Deci suspects, some interaction in the dark sector nobody has written down yet, something new enters the recipe of everything. It would be the first confirmed crack in our cosmic model in a generation, and through every previous crack in that wall, remember, an entire universe poured. The last time astronomers resolved a stubborn discrepancy in this number's family tree, the universe acquired galaxies. The time before that, it acquired a beginning. Whatever walks through this crack will be worth the century we spent finding it. I will admit to a private suspicion about which outcome we will get, though I hold it loosely, and so should you. The history of this number is a history of discrepancies that turned out to be doors. The mismatch between Hubble's first value and the age of the Earth was a door, and stellar astrophysics walked through it. The mismatch between the two Cepheid families was a door, and the size of the universe doubled through it. Decades of supernova measurements that refused to show deceleration were a door, and 2/3 of the universe walked through that one. Discrepancies in cosmology have an excellent track record of being messages rather than mistakes, and the current one has survived more concentrated firepower than any measurement dispute in the field's history. But the universe is under no obligation to my sense of pattern, and the next few years of sirens and surveys will tell us regardless of anyone's suspicions. That is the whole charm of this subject. It answers, and whichever way it resolves, pause on the strangeness of the moment we happen to occupy, because it is almost suspiciously generous. Dark energy and matter, one fading as space empties, wax and wane on completely different schedules, and yet we exist in the brief cosmic era when the two are comparable, the only era in which the expansion's change of character could even be noticed. We arrived while the microwave background still falls on our antennas, while 19 of every 20 galaxies, though already beyond reach, still shine in our sky, while the universe's birth certificate remains legible, and its speedometer, however disputed, can still be read at all. The far future's astronomers, you will remember, inherit a sky that lies to them. We inherited the one era when the universe tells the truth, and we have spent it, fittingly, arguing over the 6th decimal place of that truth. I can think of no more human way to spend a privilege. So here is the terrifying reality of how fast the universe is expanding, said plainly one last time. The universe is running away from itself at 73.5 kilometers per second per megaparsec, or 67.4, and the gap between those numbers holds either one small human mistake or the next revolution in physics, and nobody alive tonight knows which. Most of everything has already moved beyond reach forever. The engine doing it may be dying, and the ending of the entire story, stillness, tearing, or fire, will be decided by a number that fits on a postage stamp, a number your species discovered within living memory, and will probably settle within your lifetime. And yet, notice what the same number promises: tens of billions of safe years in every direction, gravity holding every star you have ever seen exactly where it belongs. The expansion will carry the far galaxies a little farther tonight, while you rest, quietly, harmlessly, the way it has every night of your life. The stars overhead are bound to us, and they are going nowhere. The universe is running, yes, but it has left the lights on for you, and it keeps, in all things, perfect time.